the grid, we have nonlinear load connected to grid, we have the converter, so then we have a filter and cable and transformer, so we have the model of the system, show it like equivalent of the impedance of the whole connection between the converter to the grid. We can also provide the DG source as a current source. Then, so now we see that this is the general model, and now we are going to see how we can control this converter. So before we start, does anybody have any question? Is it this general structure, is it clear for you? So assuming we have a grid supplying the load, and we have a converter, which we have a source here, and we are going to inject power to the grid and support the grid to supply the load and provide the stable operating condition for that one. So based on what we discussed, this is a grid connected converter. So it follows the voltage and frequency of the system, and then it can actually support the stability of the grid. If something happening here in the voltage or the frequency, we can play with the voltage and frequency of the with the active and reactive of the injected power and keep the stability of the system. Okay. Then now we are going to initiate a controller for that one. So, Costa, what is the idea and what is the intention to provide this control technique? So, okay, I mean the idea is that, you remember yesterday I said that converter is like a vehicle. You have a Mercedes-Benz, but you should know how to drive. So controller is like your expertise to drive it and control it. You can go fast, you can go slow, you can go, I don't know, opposite side, the right side, you pass the other. So you should know how inject the power and what kind of actually power is needed. To draw a control technique for the operation of the converter, we need to have the dynamic model of the system. So in a converter, the voltage of the leg is equal to voltage of the phase plus the voltage of the neutral point. So I try to explain the control technique or design of the control technique as easy as possible. I can promise you, if you listen to it, you will learn it from the scratch. But I can also promise if you miss one part, you will not learn it. So if you don't learn it, it means that you didn't listen to me, okay? So basically, this is our converter. So converter can be connected like this one or like this one. This is the converter. Sorry. So it can be connected like this. This is my source. Source can be anything, wind, solar, battery, anything, but DC, AC. So, and it can be grid. So RL. So this is I. Okay? So in converter we have conventional converter, we have 6 transistors. So in each leg we have 2 transistors. So VA so VA is S2 VDC. So VA. So what is the meaning of this? So for example, this leg, they are complementary. It can be on, this is off. Or when this is off, on, this is off. So what happens if we send a switching actually signal to turn both of them on? Short circuit will happen. Okay? So assuming that this is on, so this should be off. Okay? Do you agree? So what is happening? So if this is on, it means that it conduct like this, and when this is off means that this is on like a, okay? So it should be VDC. VDC, this voltage is this voltage. So VA will be VDC. And the other part, when this is off and this is on, it makes this one on and open, and this will be conducting, and VA will be equal to 0. Okay? So we can conclude that in converter VA is S2 VDC, VB also is S1 S2 VDC, VC is S3 VDC. You see here? So in fact, we mentioned that leg voltage, this voltage V1M, which is S1 VDC, is equal to voltage of the phase V1 from here to here, we call it 1,1 or whatever you want, okay, plus VNM. So it can be N, and this is the neutral point for here, M. Okay? Voltage of the phase plus voltage of the neutral point. Is it clear for everybody? It's from the power electronic. I can actually somehow prove it, but it takes 1 hour. If you want, I can do it, or you can accept it. This is the basic of the power electronics. So now we see that V1M is V1K plus VNM. V2M is V2K plus VNM. V3M is V3K plus VNM. Is it 100% clear? Okay. So now we actually make this summation of this V1M, V2M, V3M is equal to V1K, V2K, V3K plus 3 VNM. Yeah? So we have a balance system. It means that V1M V2M plus V3M is equal to V1 and this one. This one will be equal to 0. But this one is not 0. V1M, V2M, V3M is not 0. Why? We have the balance system. The output of the converter should be balanced. Any idea? No. So, do you know why? Remember that coffee? I asked them that, do you know why Indian put the sugar in the coffee and do this, but Italian put the sugar, do this, and Finnish put the sugar and do this? And nobody could answer. Do you know why? I mean, yeah, they are going to solve the sugar in the coffee. Yeah, this is the just the intention. And the idea for this question is that we don't make issue, I mean simple issue big for us. The answer is they are going to actually make it sweet and drink. This is the idea, the answer. So now I ask that why this is not equal to 0 but this is equal to 0. So we see that the balance system is okay here. So in fact we have a 120-degree phase shift, so it's equal to 0. But this is not equal to 0. Why? Because if you look at here, V1M is S1 VDC, V2M is S2 VDC, V3M is S2 3 VDC. So S1, S2, S3 are different. And if you look at the switching pattern, if we just neglect the 0, 0, 0 and 1, 1, 1, it is 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 2, 3, 4, 5, 6. Am I right? This is the switching. So none of them are the same. Yeah. We have actually 0, 0, 0, 1, 1, 1. Yeah. So 1, 1, 1 and 0, 0, 0, they are equal to. So then if we consider this switching pattern, you see that we have nothing that show that in one operating condition the output are the same. So Costa, what is the meaning of 1, 1, 0? But what is the meaning? Are you Costa? Okay. Yes. Yeah. Yes, but they are complementary of each other. Okay? So when this happens, so Costa, tell me what is happening. What is the meaning of 1, 0, 0?
It is whether the switch is on or off.
Exactly. So when we say that 1, 0, 1, it means that this S1 is on, S2 is off, S3 is off, S5 is off, S2 is off, S4 is on because they are complementary, and S6 is on. Okay? So how is possible that by this operating condition we said that V1M, V2M, V3M is equal to 0? So it is impossible because the switching pattern are different. So we cannot say, so this is equal to 0, so VNM will be equal to V1M, voltage of the phase 1, leg 1, voltage of phase 2, voltage of leg 3 over to 3, okay? Very easy. You see, the control of the converter started extremely easy way. So, now we go to the next part. If we are going to actually draw a appropriate control technique, we need to consider the dynamic model of the system. Sir, what is your name? Your. Yes. J. 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 J or Ajay? J. Okay, J. Okay. So, I know your name now. J. So, do you know why we need to have the dynamic model of the system? To make the suitable control technique, to design a suitable control technique? No. Does anybody knows? Okay. So assuming that you're going to go to the tailor shop and ask to make the actually pants for you. So he should know what is the size and everything, okay? So this is like this one. So if you don't know what is the system, what is the dynamic of the system, what kind of grid you are going to be interacting, what is the angle of the grid, what is the frequency of the grid, what is the actually voltage drop between grid and converter, what kind of sources do you have? If you don't have these type of things, you cannot control it in the right way, okay? So for this, we need to have a system which reflects all the information from grid to us and from the converter and from the generation. So we call it from the generation interface and the load. Grid can be load because can be considered as a load, but it can be also just a load. Because when we integrate with the current, with the grid, we should inject the current to that one. In fact, we supply something, so grid can be considered as a load, but doesn't matter. So now we see this stupid equation, and especially for the bachelor level, it seems a little bit complicated, okay? But I know that you are brilliant, intelligent student, and you can actually make everything easy for yourself. So I can explain from this and said that, okay, this is the method, and then you go that equations, but you know, Udaya asked me to go from finish way. So I'm going to make a little bit more easy for you. So then you will see that the design of the controller for the converter is not that much complicated as it seems. So, what is that? We have a converter, yes? So we have V1M here. Yeah? Then we have R, L, and V1. Do you agree? This is what we have here. It seems like a Godzilla, but this is this. Okay? And we said that the voltage, Udaya, what is the KVL? Doesn't matter, current is coming from converter to there, they mentioned from grid to converter, but assuming from this one, I. Tell me, Udaya, minus V1M, place RI, plus LDI dt, plus V1 plus neutral point, VNM. Yeah, is equal to 0. Do you agree by this? Okay. So let's get back to that one to see that I made a big mistake or not. So, basically the direction is different. So here is from here to here, but the direction of the current, but I got from there. So let's get back to the model we have here. And because we are going to compare to make sure that this is correct or not, I. So minus V1 plus LDI to dt plus Ri plus V1m plus Vmn is equal to 0. I hope it is correct. Minus V1 plus LDI to dt plus Ri plus V1m and Vmn is equal to 0. Thank God it is correct. Okay, so you see, it's nothing complicated. Yeah? And if get back to three-phase, so we see that minus V2 plus LDI2 to dt plus Ri2 plus V2m plus Vmn is equal to 0. Minus V3 plus LDI3 plus Ri3 plus V3m plus Vmn is equal to 0. Yeah, like this. So simply transfer this to other side and write this one like this. Okay? Is there anything that is not clear for you? It's clear. Yeah, even sit down, say clear. Yeah, okay. So, now we have three-phase balance system. V1 plus V2 plus V3 is equal to 0. L di d2 dt I1 plus I2 plus I3 is equal to 0. R times to I1 plus I2 plus I3 is equal to 0. Plus V1m, V2m, V3m plus 3 Vmn. And again, we see that V1m plus V2m plus V3m equal to 3 Vmn. So Vmn is equal to minus V1m plus V2m plus V3m over 3 is equal to minus 1 over 1, 3 sigma Vmn, m from 1 to 3. Nothing is completely, if Costa is not feeling sleepy, easily can understand it. Yeah? Good. So, now get back to the equation again. Because he mentioned here this is the model of this grid connected system. And now we are going to talk about the dynamic model of the system. And let me ask a question from you. What was your name? Tutika? Ah, Grutika, I remember. Grutika, tell me. Your name is a little bit hard. Grutika. Okay, Grutika, what is the meaning of dynamic? We have a dynamic atmosphere, we have a dynamic weather, we have a dynamic professor, we have a, it's too dynamic. So what is the meaning of the dynamic? Unique, exactly opposite. Yeah, so dynamic weather means that changing too much. Dynamic professor, today happy, tomorrow angry. Okay? So dynamic atmosphere, it means that you can find lots of people are talking together, but you can also find some place that people are studying, some people are actually listening music, so you see that all people. So this means changing. Dynamic model of the system means that to see what changes and what is the impacts to increase or to reduce these changes. So in the model that we developed here, the only dynamic part is current. Because d I to dt means the change of the current subjected to the time. Okay? So the dynamic model, this equation is exactly that one. This one. So calculating the dynamic model was not hard. It's very straightforward, easy. And if someone said that I cannot actually calculate the dynamic model of the system, salute. Yeah. Then seems that he or she is not listening to this one. And then probably is a pity that said that, you know, I went to the class, but I was not in that atmosphere, and then I didn't get it, and so I cannot digest it now. So it is very easy. It seems a lots of equation, but doesn't provide something complicated. So now get back again to this dynamic model of the grid connected system. So can you find anything which impact the operation of this system, this model, grid connected converter, or this model, or whatever we have, that we cannot see its impact in this equation? So assuming that if you change the L, you see the current is changing. So let's get back to this. We have switching, we have R, L, voltage in the grid. So if the load change, voltage is changing. If grid something happen, the voltage is changing. And then we have the current. So neutral point every have. So if we get back to see that any of these parameter or variable change, the current injected from converter to the grid will be subjected to this change. Okay? So what is the mission of the grid connected converter? We are going to provide electricity injecting current to support the grid. Okay? So it can be part of the active power or reactive power. So when we are controlling the voltage and frequency, in fact, we are going to play with the current injecting from the renewable energies or storage devices to the power grid. Am I right, Rakesh? Good. So now we have this, and any things happening in the network, we can see. So it's like a tailorman now has the information about your size, and if you see, I mean, you order your pants and return back after 1 month to take it, then if you increase your size, it is not, so it is subjected to your increment. So anything happening here, you can see you have in this dynamic model. Then getting back again to make it more simple. So this is di to dt. This is R over to Li minus V1M. 1M is voltage of the converter here, 1M. So it is like a S times 2 VDC. So we go here and put S1 VDC instead of V1M. Do you agree? Okay, good. When we say that S1 means the switching of the first leg, is not the switching of transistor 1. So it can be upper or lower, doesn't matter, but this is something to say that what is the output voltage. So S1 VDC, and then we have here VMN, but we said that VMN is equal to minus V1M, so it can be S1 VDC, S2 VDC, S3 VDC over to 3. So if you go here, we replace this one, which is S1 VDC, S2 VDC. So we have a S VDC here, S VDC. Do you agree? Okay. So, and then we have actually this V1 over L, so V1 over L. And now we see something a little bit easy, but still we can make it more easier. So just we have VDC here, we have VDC here, so we try to transfer this part to there. So if you get back to C, look, we have this. Yeah, it is not complicated. Yeah, Rakesh? What is the friend name? Yes. Okay, is it clear? Yeah. How many switching do we have? 3. Why? We have 6 switch. Oh, 3 legs. Okay. Okay. So you're thinking about that one, yeah? You're not sleeping. Okay, good, good. I mean, the problem with my teaching is like this one. Always I interact with the student and don't let them to sleep. Okay, so we have D1, the current changes in phase 1 is equal to R over L times through I1, and this is the switching, and this is VDC. So we have 3 phase, we write in a single phase, yeah? Is it hard to reach to this equation? It's very straightforward. So if later they change anything, you can also follow this structure and also reach to similar equation. So when you go to read some research paper, you see that they have a lots of equation. At the end, it's nothing. If you follow this routine, all of them actually following the same routine. So it is not somehow complicated. Then you can easily understand the paper if you know what is the routine of the actually this calculation. So if I'm going to actually use this one, then I said that it is better that we call this one, because this is switch, we call it DN car. So it means that we call it switching state function, okay? So it means that the switching, the operation of the phase 1 is also subjected in phase 2 and 3. Because we have actually SM, which SM is from 1 to 3. And you see that in phase 2, the dynamic change of the current or injected current from the converter in phase 2 is also subjected to phase 1 and 3. And in phase 3, it's also have interaction with phase 1 and 2. Okay? So we call it a switching state function, and we make it even more easy by replacing in the same equation. And if you put just a different value for previous this one, so D1 car is S1 minus S1 plus S2 plus S3 over to 3. DN2 is S2 minus 1 over 3, and S3 is S3 minus D3, N3 is D3 car is yeah, it's like this. N1, N2, N3 is 1 over 3, 2 minus 1 S1 minus 1. Do you want me to calculate it? You show it, or it's clear? It's completely, yeah. So now we have a system with switching state function. So now R is a constant value because it's the parameter. L is the constant value. Where DC is the constant value. And we have ICA is the injected current from converter to the grid. And also VCA, which is the voltage of the point of common coupling. So the point that converter is connected to the grid. So if voltage change, we see that the current change also. And if L we change it, we can also probably you can see that the voltage change is reducing when we increase the L. But we cannot increase as much as we want. And if we consider also the voltage changes in the grid, it means that the fluctuation will be too high. And if we have a smaller value for the VDC, in fact, we have more fluctuation in the output current of the system. So then return back again to this equation replaced by switching state function. And for the three-phase system I1, I2, I3, we can put minus R over L times to this matrix times to I1, I2, I3. So it's somehow just repeating the same in the matrix. But here we mentioned also the switching state function we obtained from here. And V1, V2, V3 is the voltage of a common coupling that we connect the converter to that one. Is it clear up to here? Do you see that you can be an engineer later which working or have an expert in the control of the converter? Yes? You can be? Yes, okay. Shifting the mood is that much easy. Yeah? It's really, it's nothing complicated. You can go be like a prophet of the grid converter control, but the basic is a very straightforward.
Actually, before coming to this seminar, actually I was thinking that this will be very difficult and
Yes. I had the same feeling actually. But now my feeling changed actually. Arya is not here, so tell him at least it was the biggest lose of your life because you cannot be expert in this for the rest of your life. Yeah, okay. Is here? Yeah.
current is dynamic in nature and VDC is voltage across capacitor.
Mm-hmm. No, it is not the capacitor. We have this one, but we have the voltage regulator there. So it can be basically if we have we can have the capacitor, but then the problem with the capacitor is that we charge and discharge it fast. But basically for this type of technology, we use for example, lithium-ion battery, but lithium-ion battery is not fast enough. Then we have also capacitor for the transient, actually, fast transient application for the short time. Okay, but you can continue. Hmm? We use, but not for the continuous operation, for the starting operation. So because in some cases when for the dynamic operation, because then if we need the fast dynamic reaction, then capacitor is reacting fine, but the problem is that when we have big changes, then the energy can be actually discharged for the system is not enough to have a big impacts on the stability of the network. Yeah, this is the problem. So you had something to say, I forgot. What? He's not feeling well. Yeah, he was up to midnight in the street. So if I had the same actually experience, I was not feeling well. Yeah. Last night he was too active. So probably this is the reason. Yeah, he's hyper. Okay. So we can buy like a chips and this yogurt. Go to say hello to him. Yeah. So he's in the dormitory or in hotel or somewhere else. Yeah. He's lying. Tell him I said he's lying. Yeah. I had the same actually trick when I was not in the mood to go to class. I said my mom like, okay, I'm feeling bad, headache, this type of things. Yeah. Okay. So, uh, you see that, I mean, this is not that much complicated, but this is the first. It's like you learn how to turn on your car and just drive. If you're going to be rally driver like a Schumacher, then you can go faster actually. So for this reason, but I can say that for any of the controller you should start from here. So now we have the dynamic equation of the system. So we see that we see in lots of book, papers, and then they have such equation, but you don't know from where it's coming. But now we see that we know from where it's coming. So we have a three-phase system. Three-phase system is a balance, so we make it more easier, and then just the I1 plus I2 is equal to minus I3, or V1 plus V2 plus V3 is equal to 0. So by this we can easily remove this part because they are balanced system, and to reach this equation. So we call it dynamic model of the system. Now is the starting point to design the controller. So at the beginning of the class, I mentioned that to draw an appropriate plan to control the interface converter for integration of energy source into the power grid, a dynamic analytical model of the proposed model should be developed. Now we developed it. We have the dynamic model of the system. So just one probably comment is that this is the dynamic model of such a system. So then in some cases, in a state of RL filter, you can use the LCL filter, you can use the different types of the actual filter, but it doesn't provide anything. You can just add some equation more and then follow the same thing and reach the same, a little bit different, but at the end you have DI and something like this, and just you had some capacitor, and that's all. Okay, it shouldn't be that much complicated, but I remember that I used this one in this paper, a control technique for integration of DG unit to the electrical network, IEEE transaction in industrial electronics in 2013. I use it, it works very well, and then I implemented by hardware, so it provided a really good answer. THT was less than 5%, it was 2 point something, and it works very well. So if you don't have any strong reason, then you can use the same. But there is one thing that, for the very high power or very low power, the types of the filter can be different. So it is not applicable for all level of the power. So basically, this type of technology filter actually is more feasible for the medium power. Yeah. So, Siddhant, if I put the LCL filter, you can make the calculation, yeah? Yes. Can you come to do it? You can try no. You said yes, without hesitation. Okay? So probably we can just see what is happening. So we have a converter, V1M, and we have R, L, C, L, V1. So L1, L2, C, you can neglect this R. Can you make the KVL and KCL for this one? Yes or no? Yes. Okay. It's that much easy. But just you add the C here. Okay? It doesn't provide, so you have also IC, so I converter, I grid. So I converter is IC plus IG. Then you make your KVL. That's all. And you can actually use this one C dV to dt for the current. Okay? So it is not that much hard, and don't make everything complicated. You see, wow, it was different. I talk in RL, now it's LCL, and so, yes? VDC? No, DC link voltage, yeah. It's like a, so assuming that you have a wind, we shown yesterday. Yes. Where is the, okay. Yes, it's here. Mm-hmm. Yeah, it is, look, basically, so assuming that we have any power, okay? So it is like this, okay? This is the power. Can you see it? This, okay? So it's like a power of wind, okay? Then we apply to this, for example, capacitor, okay? Then we have this one, I, which is C dV to dt, okay? Then we have P also, VI, okay? So then V is equal to P over 2I. But the problem is that this V is not regulated. So for this reason, we need the regulation, voltage regulator here, which can be also based on the extra DC-DC converter, adding in the DC side, or probably you can actually use the, somehow we said that, for example, the VDC we need is 600 volt, but we have actually some fluctuation. Then in the voltage of the DC, so we said that reference voltage is 600, but the voltage that we have is VDC is not 600. So we have some problem here. Then the compensation by PI controller is needed. And then you have actually some equation which create a ID for VDC. This ID for VDC can be added to the control loop of the current, and after transient time, we reach the DC value, regulated DC value for the DC side. So let me show you in a real case. Yeah, this is a real case simulation. We had 600 volt was the input that we had from the power from the, and we provide actuation for the control DC. After this transient, you see, transient time, it the constant value. So basically, they are some, but it depends on how much you're sensitive. You can basically say can inject to storage, and then it can be used as a of the converter. For example, this type of transient cannot be used sensitive load, but or cases that it is not for the residential, it doesn't provide any problem for the loads. So you can use such a technology by regulating the DC voltage. But you consider that this is very unregulated power because we have also controller in the speed of the blade, so it cannot go very deep to very high. So, any questions so far? So up to now, we get the idea about the